So hello everybody. So I'm here to talk to you about what we do at Qarnot. So I'm Clement. I'm the Chief Technical Officer of Qarnot, and I will talk to you about what we do with district heating networks. So we love to show these two pictures because on the left side you can see the cooling system of a data center. So the main goal is to create cold to remove the heat from the server, and on the right side you can see a district heating network. So we are quite confident that we can mix both of this, and how we do it, I will show you. So one thing which is very interesting with district heating network is that across the time, the temperature needed in district heating network is going down. And now, on the most modern district heating network, you need temperatures that are lower than the temperature that you can get from a CPU. So that means you don't need to prime the heat with heat exchanger or with heat pump to produce heat for the district heating network with the CPU. There is also interesting thing with district heating network is that a lot of them have cogeneration. So that means inside the district heating network you have electricity and heat production, which is interesting if you want to power some IT equipment. And another very interesting thing is that across the Europe, the district heating networks are dependent on gas, which is a little bit problematic, especially during these times. So how we do it? So at Qarnot, so we are a French small company, and so we build district heating hardware that can be used to power the district heating network with IT equipment. And we also build a cloud computing platform on top of it, so it's easier to run the servers for customers. So how we do this? So we designed this system. So it's at the same time a compute cluster and a boiler. And so there is no pump. There is no cooling need, no water consumption, and 95% of the electricity consumed by the system is reused in the water, and we can produce hot water at 65 degrees, which is very interesting because this is the amount of heat which is interesting to be valued. So this is how the system is working. So we redesign a completely different thing. So this is not a traditional data center rack server. This is our own design. It's cold plate, and one of the specificity of the system is that we have 20 millimeters pipes, so we can run tap water in it at a very high flow, so 1,000 liters per hour, sorry, which allow a very interesting heat transfer capacity. So I will talk to you about one of the sites that we have. So this one is in Finland. This is a site that we operate with one of our partners, Vatajankowski. So it's a small city in Finland. There is 17,000 inhabitants in this city, and the district heating network is a 24 megawatt heat and power generation. And so the temperature for this district heating network is between 45 and 75 degrees, which is almost what can be achieved with our system. What is interesting in this city is that there is also a swimming pool that we are heating with our system. And so we have some system inside the swimming pool, so it's a compute cluster. And with the IT in it, we can produce 50% of the heat needed annually by the pool. And so we have some customers that are running their computation on this cluster, and so this will produce heat for the swimming pool. So this is the main site that we have. Today we have deployed 100 kilowatts of IT in it, and we can go up to 2 megawatts of capacity. Today it's a 15,000 cores cluster, which is mainly used by a French bank for risk analysis and Monte Carlo simulation. And we know that we can expand it to 2 megawatts, which is the need of it even during the summertime in this city. So what is very interesting in this project that beyond IT and what we do, there is also some very interesting things. So this is a battery, a sand battery, a 100 ton of sand. And at some point in Finland, the electricity can be very cheap or free. And when this is the case, they can heat up the sand, and then they can use the heat from the sand to prime the heat for the district heating system. So we love this project because it integrates us in a very efficient and green way of producing heat. And so we know there is multiple opportunity to deploy this kind of system in Europe and in the US because we know that even during summertime, there is need for it. So for example, in the site that we use today, we know that even during summer, 2 to 5 megawatts is something that is needed. So it's not a big data center, but it's more like edge and medium-sized data center. We also know that the gas dependency is a problem, and being able to have renewable or green energy is something that is very important for the district heating providers. And so being able to use one source of energy to at the same time produce heat and produce compute capacity is something which is very, very important, especially with the price of energy today. And so on the last slide, I just want to show one of the sites that we have. So this is the different module that we deploy in the power plant, and this is the OCP server that we integrate in our system. So we work mainly with CPUs today. But we are also planning on integrating GPUs and ASIC for our systems. And so regarding call to action, so you can contact me. You can also see downstairs we have a poster which gives some details on how our system is working. And we also try to participate in a heat reuse OCP workstream. So this is it. If you have any question, I would like to answer them. Okay, so yeah.
What was your exit temperature? What was the temperature you were able to achieve with the system?
So with the system today, we are able to achieve 65 degrees Celsius for the output temperature of the system. So it will depend on what kind of CPU we are using, because it's mainly it's direct liquid cooling, so it will depend on the maximum case temperature of the CPU. And so today we know that there is a delta of 18 to 20 degrees between the maximum temperature of the case of the CPU and the temperature that we can get in the water. But we are working in reducing this delta as much as possible.
In the setup, how does the thing with the sand work? The storage?
Oh, this? Yeah, so it's 100 ton of sand inside, and inside you have a loop, a water loop. So when the electricity is free, you can just heat up the sand, and then if you want to take it from the sand, you just have to make the water flow through the sand. And so in this case, it can prime the temperature of the water by 25 degrees.
So this wasn't built just for you, this is used for general storing the power?
Yes, this is not just for us, but this is a quite efficient way to prime the heat from our system before injecting it in the district heating system.
Please approach the microphone.
I have a question. What happens if the swimming pool, for example, needs maintenance and has to shut off?
Yes, that can happen. So if you see on the graph on the right, you can see that 1 week during summertime, they have to turn it off. So this site is used in our computing platform. So this is a generic computing platform for example, for 3D rendering or anything like this. And we have multiple sites, so in France and in Finland. And so if one site is not available, we will send the computation on the other available sites.
Please use the microphones. Thank you, sir.
Sorry?
Could you please speak in the microphone, sir?
So you would take the site down to stop it from producing heat when the pool needs to shut down for maintenance, for example?
Yes, yes.
And just to note, the folks at Qarnot have been really fantastic. They just have listed these solutions on the OCP marketplace. Highly recommend getting to chat with Clement. They've been really forward-thinking on a lot of this.
Thank you, Steve. Okay, thank you.